In our previous discussion, we established the microscopic criteria for electrical breakdown via the Townsend mechanism. Today, we will examine the macroscopic, steady-state plasma that forms immediately thereafter, the normal glow discharge. This is a self-sustaining, low-current, low-pressure plasma characterized by a distinct, luminous structure that provides a direct visual representation of the underlying physical processes. Once the Townsend criterion, gamma, E⁻D, 1, greater than or equal to 1, is met and breakdown occurs, the discharge does not remain a formless spark. Instead, it rapidly self-organizes into a stable configuration with a nearly constant voltage drop, largely independent of the current. This is the defining characteristic of the normal glow regime. Its most striking feature is the series of alternating light and dark regions between the electrodes. These bands are not arbitrary, each corresponds to a specific zone of particle kinetics, energy transfer, and collisional processes, forming a spatial map of the discharge physics. Let us now proceed with a detailed, spatially resolved analysis of the structure of a direct current glow discharge, from cathode to anode. Immediately adjacent to the cathode surface is the Aston dark space. This is a very thin, non-luminous region. Its darkness is due to the fact that the secondary electrons just emitted from the cathode have initial energies close to zero. As they begin their acceleration in the electric field, their kinetic energy is, for this brief distance, still below the excitation threshold of the gas atoms. Consequently, collisions are primarily elastic and do not result in photon emission. As these electrons continue to gain energy, they enter the cathode glow, a thin, luminous layer. Here, the electrons have acquired just enough energy from the electric field, typically a few electron volts, to cause optical excitation of the gas atoms upon collision. The direct excitation of these atoms produces the characteristic glow. It is important to note that the ionization probability here is still relatively low. The electrons then traverse the most critical region for discharge maintenance, the cathode dark space, often referred to as the Crookes dark space. This is an extended, non-luminous region characterized by a very high electric field gradient. In fact, the majority of the applied discharge voltage is dropped across this zone. Here, electrons are undergoing rapid acceleration. They gain sufficient energy to cause efficient ionization, but their energy distribution and the collision cross-sections are such that the probability of excitation, which requires a specific energy threshold, is minimized. This results in prolific generation of electron-ion pairs, the Townsend avalanche, with minimal light emission. The positive ions generated here are accelerated back towards the cathode by the intense field, and their bombardment is the primary mechanism for sustaining the secondary electron emission quantified by the coefficient gamma. Emerging from the high field region of the cathode dark space, the electrons enter the negative glow. This is typically the brightest and most intense region of the entire discharge. The electrons here have a broad energy distribution, including a significant population with high kinetic energy acquired in the dark space. They now undergo a high rate of inelastic collisions, leading to intense excitation and, consequently, strong optical emission, as well as further ionization. This region is a plasma, with high densities of electrons and ions. Following the negative glow is the Faraday dark space. This region marks a transition. The fast electrons from the cathode have now dissipated most of their energy through the numerous inelastic collisions in the negative glow. Consequently, the electron population in the Faraday dark space is largely thermalized and lacks the mean energy necessary for efficient excitation. The electric field in this region is weak, and electron motion is more diffusive than directional. Finally, we reach the extended positive column, which fills the remaining space to the anode. This is a region of true, quasi-neutral plasma, where the densities of electrons and positive ions are nearly equal. The electric field here is low, weak, and constant, just sufficient to drive the ambipolar diffusion of charges and conduct the current to the anode. Its luminosity is a secondary effect. Crucially, the length of the positive column is not fixed, it adjusts elastically to the distance between the electrodes. If the anode is moved, the positive column expands or contracts, while the cathode layers remain essentially unchanged. This reveals a fundamental point: the cathode layers are electrodynamically essential for the discharge's existence, while the positive column is primarily a conductive filler to complete the circuit. Regarding operational modes, we distinguish between two key regimes. The normal glow is characterized by the cathode glow covering only a part of the cathode surface. In this state, the current density at the cathode is constant, and the total voltage remains stable over a wide range of increasing current. If the current is increased beyond a certain point, the glow will eventually cover the entire cathode surface, marking the transition to the abnormal glow. Here, the current density must increase, requiring a higher electric field and, thus, a rise in the discharge voltage with any further increase in current. In conclusion, the DC normal glow discharge is a complex, self-organized non-equilibrium plasma whose intricate visible structure is a direct manifestation of its underlying physics. The alternating dark and luminous regions correspond precisely to zones of electron acceleration, ionization, excitation, and thermalization. Understanding this structure is not merely academic, it is foundational to the application of glow discharges in numerous technologies, including plasma etching, sputtering for thin film deposition, surface modification, and the operation of various gas lasers and lighting systems.